Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Future Friday, we're going to talk about energy mix, the true silver bullet. So let's dive deep into it. So first, what exactly is the problem? Well, if we keep going as we are going, meaning burning fossil fuel, we're going to be cooked. And at this point in time, if there is any doubt about it, it's just wasting time. For example, we have like multiple space agencies exist at this point in time that has that sort of what you call long-term data. And I do not mean, okay, 5-year data. I mean 50-year kind of data. ISRO has it, NASA has it, Roscosmos also, but I'm not sure whether they have data before 1992. Did they copy-pasted data from Soviet Union or not? Maybe they do. But reality is all data points to the same thing. If we keep adding CO2 at the rate that we are adding, we're gonna be cooked. Like it's not debatable at this point in time. So we have to change it. And here's the deal. There is a trick. The trick is that I can show you India's map, like India is getting hot and this is becoming a news that it's brutal, it's getting hot. Somebody can trick you. And again, people have tried to do that with Germany also. Is like, oh, it's not real, because again, in 2009 also we had this sort of temperature. You have to pay attention to laws of physics. You must have heard the statement multiple times that average global temperature will rise as high as 2 degrees Celsius in short term, 4 degrees if we do not do anything. That's a factual thing. But here's the peak temperature will not change that much. Like, wait, what? Yeah, when I say India is getting hotter, I do not mean the peak is crossing. No, that's not happening. The bottom part is climbing. That's the problem. For example, during a day, there will be a curve. Basically, sunrise comes up, the thing starts to heat up, and sun starts to go down below the horizon. It starts to cool down, right? That cool down is not happening. That's the first thing that happens, because here's the deal. At high temperature, let's just say a landmass, let's say that landmass cooks, it's like 50 degrees Celsius. Here's the deal. It has 50 degrees Celsius of photon flux. It's much easier for it to dump energy out. But if you are at 40 degrees Celsius, it's not that easy to dump heat out. And that's what's cooking us. That's basically, it's Newton's law of cooling. I'm pretty sure all of you must have studied that in school, that let's just say if your ambient temperature is 25 degrees Celsius, you had a glass of water that is 100 degrees Celsius, that like hot water, that will cool very quickly for first few degrees. That's what happens when the peak temperature rises. World can handle that. How we are being cooked is the bottom temperature is going up. Basically, the night is no longer as cold as it used to be. The average temperature, the lower end is not low enough, so the average is climbing, even though peak is same. It's like, this was like 50 degrees Celsius once in a while, whoa, and average was like, 40. Now it's like average is 42, the peak is still there, but now the global average is like sliding upwards. That's the main issue. We are cooked and we have to fix this. But here's the problem, why it's not that easy. Well, our needs and demands are ever expanding, and it should be ever expanding, because again, we really ought to, that's our main goal. That's why we have this 1.5 kilogram of brain. It's ought to keep increasing our quality of life, and for everybody, not just like, oh, they achieved it, so now they keep their air conditioning running and we can't add more air conditioning because it will hurt the planet. Yeah, that's not fair. So fundamentally, life quality should expand. We have to figure out a way to do it without causing harm, and then do it while actively cleaning all the mess that we did. Again, that's normal. A child is born, it learns to poop in itself. Then over years, you have to teach it to poop in a toilet. So we have to do that. Humanity is going through that phase. So, and the core part is, the core fact, why the heck humanity messed up this bad? Because we relied on a single tool. This happened because we thought fossil fuel was the answer. Like one thing to rule them all, we died. So that's the critical aspect. We cannot go in the future if we still have this mindset. That mindset is the problem, not fossil fuel. Fossil fuel was a tool. If we would have weaned off of it, and let's just assume, let's say in future we do wean off of it, it would be great. It's like, oh, this was a tool that it was diaper technology. It taught us everything. We learned, we created a better technology replacement, and then it was like, it was a messy era. We kind of cooked everything, and then we're like, okay, let's fix it. So fundamentally, can it be done? That's the desire part. Can it be done? Yes, but it has to have multi-prong attack. You cannot, this technology was, again, you will go back to the same problem. You will go back to the same problem. It has to have multi-vector attack. All vectors have to be boomed at the same time. Only this we can start to cool things down. So let's come to the first easy target, which is electricity. Now, what we need in electricity? We need 3 core vectors. Cheap is the first thing, because again, you want quality of life to rise. Cheap electricity matters more than 24/7. Cheap matters, Abundant, meaning if you want to expand, like let's just say I want to put a steel plant or whatever have you, and you need bonkers amount of electricity, that should not be a limiting thing. Abundant and available. Available meaning 24 into 7. So these three are the vectors. Now here's the solar is my favorite. Solar is cheap. Everybody knows that. Like the world that we live in was unimaginable in 1990s. Like if you have told anybody in 1990s that you're going to have a large portion of your civilian population having their own solar farm, and that makes enough electricity that they are running their meters in reverse, and the only reason, like because of the tariff mismatch, as in like you buy electricity at higher cost, sell it at lower cost, like that's why they are not printing money with this. Nobody would have believed you, but that's normal. That's normal in India now. That's normal any place where they do not have too much bureaucracy. It's not normal in Germany. They have stupendous amount of bureaucracy. But if it's solar is not cheap in your country, it's bureaucracy. So cheap part done, abundant. Here's the deal. If you cover every single human structure that exists, I do not mean mow down forest or something like that. Human structure, we good. More than our energy consumption. Like we will be good, we will be sorted, we will be done. And problem, it's not 24 into 7. That's a problem. Wind, 24 into 7. It will work 24 into 7 if you select your site properly. It's not cheap, nor it's stable. As in, wind farm has this paradox. Again, solar crossed this. Solar crossed this, give or take 2012 to 2015. As in, making a solar panel costs less than the carbon footprint of its energy. As in, there is no other way of making that solar panel other than solar panel itself. Meaning, if you are making a solar panel, it let's just say produces 1 ton of CO2. Here's the deal. You could not just release 1 ton of CO2 and still make the solar panel, no matter what you use. You use coal power plant, it will release more than that. If you use natural gas, it still will release more of that. Anything you do will release more CO2. Basically, that's what we call carbon negative. It has reached a point where making more solar panel, using the energy of the solar panel, actually starts to slowly takes us towards basically panels becoming a negative thing. Now, what about mining? Yeah, that's the only thing remaining. Other things are already sorted. How the heck that happened? Yeah, panels started to last longer. There was a time panels were only rated for 5 years. Now we have 25 years. They were only 10% efficient. 22 is my rooftop. And that's without jumping into multi-junction or PVT. So solar crossed that. Wind is crossing that. Problem with that is that it requires to be big. Physics does not like tiny wind turbines. Like it just does not like it. You cannot see a future where every household has tiny wind turbines, no matter how many YouTube video you see, how many Facebook, LinkedIn, Instagram posts you see. It will not happen. It will not able to justify itself. And wind turbines do not like to be small, as in like few megawatts. Yeah, you might as well not make it. Again, make it. It's better than releasing CO2 directly. Indirectly releasing still matters. But here's the deal. If you keep making it bigger, generally above 10 megawatt per, you reach a point where it's starting to become carbon negative, almost like solar panel, meaning the energy emission consumption that was done to make this, it made more. We are reaching there. 12 megawatt, 16, like General Electric Halide X, if I'm not mistaken, that's the 16 megawatt. That should be almost reaching a point where it's like, if it works for 10 years, it will be carbon negative. So we are reaching there. It's almost going to happen. And again, it's 24 into 7. So your grid will always have inertia. And it's stable, as in like, it will be there. It's just not abundant. Meaning some months you will get YOLO amounts of basically electricity. Some months you will be like, eh. So wind. Again, solar alone is not enough. Wind alone is not enough. Hydro. Now, hydro dams does make sense, like 24 into 7 into 365. However, it's not long term. If you know anything about China, you know anything about India, you know anything about Iran, you know for a fact that the more dams you build, the quicker the river dries out. If you're not familiar with it, please study hydrodynamics. If you want to condense addition of it, a river is an equilibrium system, meaning the water intake and the water travel and the water that is going to the sea, it is at an equilibrium point. When you make a dam, you break the equilibrium. What is that equilibrium? How much area of that river is exposed to the sunlight? When you make a giant wall, like let's just say Three Gorges Dam, you go like, bam! You create a massive reservoir that increases the surface area of that river exponentially, like 10x. Now here's that surface area exposes the water. Same amount of water. Water did not change. The amount of water did not change, but the two vectors boiling it expanded. One is wind. How much wind can leach away vapor from it? Second, sunlight. How much sunlight can fall on it? Yeah, both vectors went through the roof. you're gonna boil bonkers amount of water before the reservoir. As in, like, reservoir is here, like dam is here, this side, reservoir side, whoosh, boil away. What about downside? Because you shrunk the total volume, those water no longer have the inertia, thermal inertia. Basically, it's much harder to boil 100 liters of water compared to 10 liters of water. Now, if you shrunk the flow, sun is like, bro, what is this? Psst, boiled, done, gone. So downside disappears, this side shrinks. And again, China built dams. And how do you know this is bad? Here's the pay attention to that civilization bridges. If they built bridges on a river, if the bridge is high, pillars are high, they have ratings, like generally all companies do this. They put a marker where the normal flood level is at 3 meter, 5 meter and all that. And all you are saying is sand below it. Yeah, they did not anticipate the river disappearing. It does happen. India has way too many of that. Iran went YOLO on it. So general calculation is 30 years. If you're closer to equator, it will happen in that time frame. If you're further than equator, or you are in one of those unique scenarios where you have very few dams, way too much rainfall, you could survive. But most places, especially largely populated places, yeah, river bye-bye. You put dam, river bye-bye in 30 years. Again, it could take longer. It could, you could have some weather pattern changes where it's like, okay, this river merged with this or something else happened. But it will happen. It's not a if, it's when. And that's the first calculation that is done whenever a dam is built. 30 years. We humans do not have memory after 30 years. So we'll forget that we are the one who boiled it away. Like, people warned China. Chinese people, do not build 3 gorgeous dam. It will boil it. And in 2020, why the heck we are seeing a rock in this river? Which, like, bridges is kilometer high. Not kilometer, like, you get the point. Like, you can put a decent sized building below it. They never expected water to go so low that you can walk. So hydro is there, but it's not long-term stable. It's something that you can add as a sprinkle. What about nuclear? Again, nuclear is good in small doses, like if you have some small parts, but that puppy is risky AF. You do not want too much of it. And again, understand that we destroyed humanity because of that, trusting on one technology above all others. We have to mix it. So nuclear in small doses is good. Too much? Yeah, we did. Like, you want example? France, so much nuclear power. Yeah, they are not prosperous. They are not manufacturing everything. Electricity is not cheap there. Why? Nuclear requires rivers. They boil river away. 2022, they had a scenario where they had to throttle the nuclear power plant because they were boiling. Again, they had dams, and whatever tiny rivers were there is like, yeah, if we keep running reactor at full power, yeah, there won't be even a liter of water left in the canals. That's how bad it got. And China never shuts up about nuclear project. Most of their energy still comes from coal. You cannot change that because nuclear is not cheap nor abundant. It is available, but in small doses, it's good. It gives you a grid inertia. It gives you something that you can rely on. But other than that, it's like, it's very risky. And it generally goes boom when you turn it off. That's why, like, Chernobyl had to do that testing. It's like, hey, what happens when you turn it off? Yeah, it goes kaboom. So because if you reduce all the fission, you also run out of power, as in, like, your turbines are not running, but you still have heat in the reactor, enough heat that you need a pressure pump to feed the power. If you do feed the water, cooling water, if you do not, steam will push it out, and that could last 2 years. Some designs. That's why cooling pond exists for spent fuel. Understand that there is a reason why you have swimming pool for spent fuel. So you press the control rod button, fission goes down, daughter products are still there, and they are still giving you off energy, megawatts of energy, and you have to have pressurized pumps. And they had to do the test. It's like, because backup generator will take time. You push the control rod, turbine cannot have load at that point in time, so they have to disconnect the turbo generator from the massive grid, but it will still be spinning. So at that point in time, divert that power to the pumps, so you can give pump enough head spin, enough time, so backup generator can start. Once that is, they should take over. That's what failed in Fukushima. Basically, they had to do testing because it is compulsory. Because again, earthquake happens, terrorism happens, boom happens, sabotage happens. They were very worried about sabotage. So they had to do that testing, and that testing caused boom. Fukushima, earthquake happened, tsunami happened, boom. Backup system is like, bro, I got you, fam. Shut down, manual shutdown, no override possibilities. It's gonna shut down the reactor. Cool. Reactor went to boom. Why? Japanese ego, all the backup generators were under basement, below sea level. Water flooded it, backup generators offline, no more high pressure pumps, and boom, boom, boom. So that's why small doses, good. Large doses, no good. Geothermal, again, it's also becoming a very decent thing. And if a lot of companies that are trying to crack it, if they can crack it, that will be a big, again, not a soul, but big puppy. Biogas, again, very decent, very suitable for a lot of remote areas, and and again, you have to do biogas because methane is worse than CO2, so you have to do that. Biomass, again, as a good add-on tool. Add all of these, puppy. Then you have a country that's grid is resilient and not burning the planet. One of it will not be enough. Add all of this, it will be. And again, how can we do that? You can't send electricity very far if it's AC, but if it's DC, high voltage direct current, India is master of that. Like, there are only two countries that have like GG scale HVDC. Both are India and China. China has like 12 gigawatt at 1200 kilovolt. That three gorgeous dam. India has the largest multi-connection point, meaning HVDC A, HVDC B, HVDC C. That does not exist anywhere in the world as of now. It could have been opened recently, but generally most are backhauls, like you're connecting France to this, France to Germany and all that. But multiple connections, like the same line goes through three places, that does not exist. India has that. And India's is also a big one, 800 kilovolt, big puppy, DC. So that does allow you to send power kilometers away. And again, you must have heard people who are trying, what if we cover Australia with solar farm and then connect it to Europe? It can be done with HVDC. So that's how you solve it. Do not rely on one thing. Mix and match all of the variables. Now you get resiliency. Use HVDC, which again, we have the technology, and that allows you to have the oomph necessary to handle situations. Now, what about storage? Now, storage is a good thing. It makes energy stable. Now, be mindful. Storage was built before this renewable thing. It was always a desirable thing to have, because if you do not, you have to take the whole country offline in order to do maintenance or upgrade. So there was always a time. Sometimes they had peaker plants taking the role of it, but storage was something that people took seriously, specifically during the 1970s era, what we call a nuclear fever, because they realized everybody wanted to make nuclear plant at that time. If they did, none of the plant will make money because there will be so much overcapacity. So they're like, okay, we have to make base load, little bit of buffer, but how the heck we take care of the peaks? The idea was the peaks are peaks at the day, but at night it goes down. So you have a lot of energy at the night time. What if you can store the energy at night and during day peak, you dump it, and your power plants can work at 100%. So you get very quick ROI. Here go, pumped hydro was created. Multi-gigawatt hour. And these puppies are ancient, as in like they have been working for 40, 50 years, non-stop. And they can work hundreds of years. As long as you can maintain it, it will last forever. And many of them are closed loops, so do not even affect any water body. So we have to learn from it. Again, we've gone through this, like we've been done. Problem is sorted. So battery is great for house and small scale, meaning it's a very good and wise thing to do for nation to have almost middle class of household for 5-unit battery, 10-unit battery, 20, 30 unit is like, we good. Grid stays there, does not stay there, it does not matter, we good. Small scale was as in like some schools, some hospitals, some villages that do not have very strong grid connection. It makes sense in small scale. It does not make sense to make a gigawatt hour. It's unwise to do so. It's because again, it consumes batteries. Batteries are not like, okay, you put it once and you forget about it. It's not that. It's not pumped hydro. This is the Indian pumped hydro, by the way. There are many. So it's not something you built once and you just service it and maintain it, forget about it. It's something that consumes. So in 25 years, it will pile up. So closed loop pumped hydro at large scale, that is going to take care of the bulk, puppy. As in like, oh, you need 10 gigawatt hour? We got you, fam. We got you. China has that. So closed loop pumped hydro is the big puppy. That's going to take care of a bulk loading. Then we have old thermal power plants, meaning India has a lot of coal power plants that have to be shut down. There are generally two primary reasons of shutting them down. One is coal is becoming expensive. And again, solar is getting cheaper. So you can't sell electricity if the fuel intake is expensive. And people will not pay for expensive electricity. That's why I keep saying it has to be cheap and abundant. So we have to decommission so many coal systems. And again, I am happy with the reduction of that soot, the reduction of that fumes. I'm happy with that. But you have so much infrastructure. And again, some places have to be shut down because of water shortage. So why not convert those puppies into batteries? And how can you do that? Well, first advantage is it's cheapest. Why? It's already there. Everything you need is there. All you have to add is take away the coal burner boiler, yeet that puppy away, or maybe just keep one of them. Like generally coal power plants have multiple units, so keep one of them and have a ginormous insulated graphite block that you heat up during daytime, some solar and wind and all, whatever have you, and it keeps steam cycle running because it can go to high temperature as in 1500 degrees Celsius, and during night time it starts to cool down. This is E2S power. This is in India, Asansol. It's a small scale demonstration. The idea is very simple. You convert coal power plants into a battery, and it has double benefit. First is it will give you grid inertia, meaning you must have paid attention to the news that Europe was, especially some smaller nations, were facing the issue is like, hey, we are adding so much wind, we have so much wind power. Oh, our grid are going kaboom because it's not stable. So they took old coal power plants, thermal power plants. They're like, hey, what if we throw away the turbine, put a giant flywheel into it, and we call it synchronous condenser. That's how they got the inertia back. We are doing one step extra. Why not make it into battery? So that will give us grid inertia. Again, infrastructure is already there. The turbine is there, steam system is there, the turbo generator is there, the grid connection is there, the substation is there, trained employee, all of things are already sorted. Like it's a pre-built system. All you have to add is a big battery box, which is not even a battery, it's just a graphite with insulation. And the bigger you make it, the better it becomes. Surface area to volume ratio. And this is the primary reason why we use AC electricity. It's not, transformer is a very good thing, but this is the primary reason. Meaning, if you imagine let's say steel mill, and they plug on their main furnace that can draw as much as 10 megawatt. How the heck you're gonna feed 10 megawatt? They're not gonna pick a phone call. It's like, yo, my man, give me 10 megawatt of energy. You're not gonna do that. So how the heck power plants can provide that extra 10? Well, where does that energy come from? It comes from the transformer. Transformer leaches it from the magnetic field. Magnetic field leaches it from the high side magnetic field. Then it goes back to the turbine. Now, turbine, basically where you're leaching from? You're leaching the energy from the stator. Stator tries to leach energy from the rotor. Now, here's the rotor is hundreds of tons. That's why we want big, massive puppies. So when you have hundreds of tons, no matter what you do, you cannot slow it down. Like you cannot go like, okay, I'm gonna draw 10 megawatt extra out of it. Let's just say that rotor was giving you 500 megawatt and you're like, okay, 10 megawatt extra. It will not even care. It will like, bro, oh, okay, let me react. And that's the whole point. That's how this system works. Basically, the moment demand rises, computer will detect, hey, that 50 hertz is slowing down. It's becoming like, no, basically 49.9. Computer will notice it's like, 49.8. Okay, increase the steam pressure. That's how computer reacts, because without that mass slowing down the reaction speed of like that inertia loss, computers cannot work fast enough. And be mindful, we used to do that with analog systems, like actual galvometers. Sorry, I keep forgetting myself. You heard that term like balls to the wall? That was that ball governor that used to spin on a rod. That's how we used to maintain it. So 50 hertz, that's how we do it. That's the big benefit of it. And it allows you to have enough buffer time where it's like, okay, increase the pressure. And otherwise also, for example, let's just say you turn off the plant. Now you had so much extra steam pressure. Here's the deal. From steam side, it's like, I'm gonna spin you harder. It's like, bruh, wait. It will, it will low. Then the computer will like, okay, easy, bro, easy. So that's why grid inertia, and you want this sort of inertia, not, okay, call General Electric and ask them repair their black magic technology known as grid forming inverters. I'm like, I do not trust those things for a national level thing. And again, we have this. We are gonna decommission it. Why not use it? It's there, it's cheaper. So greener. And heat, again, heat can be utilized for other things. And the essence that we are trying to achieve is distributed robust networking. You do not want a country where it's like, oh, one substation goes away, everything falls apart. It's like, no, we have multiple nodes of power, multiple modes of generation, multiple modes of energy storage, all of them working together. That gives your country stability, economic growth, and jobs. You do not want to trust one thing. Now we come to the thermal part. Most of energy that we are consuming is being consumed by thermal systems. One way or the other, either you are heating something up or you are cooling something down. And we have to understand that it's far better to store the energy directly in that method. For example, let's just say you're like, okay, I'm gonna treat this metal, and that, let's say, requires like GG amount of time, let's say 1000 degrees Celsius. Here's the deal. Right now, if you talk to people, it's like, okay, it consumes this many megawatt hour, right? And you're like, okay, we need this much energy storage to buffer it from the solar. It's like, no, you don't. No, you don't. All you need to do is basically have that heat source, basically your thermal elements, dump heat into a buffer that is directly storing the thermal energy with minimal loss, and then you keep using it. That way, you no longer need a giant chemical battery. That's the essence of it. Because direct energy storage, you can make it huge, without too much cost. So for example, thermal energy direct storage will be far better in multiple things. For example, let's say industry. You're talking about some big industry that requires like bonkers amount of temperature, let's say 500 or 800 degrees Celsius more, or even like, E2S system. How would they store that energy? You can use electrochemical systems, stupendously expensive, and not to mention they are consumable. Or you can have a graphite block in a big ass tub. And again, big means big, as in like multiple meter big. And then your daytime, when you have surplus of solar, you dump energy into those puppy, they heat up, and they throttle the output to your final process heat. It's like, okay, this is much heat is going there. And this slowly starts to heat up or cool down, and you have the output. This is far more cost effective than, okay, you need this much, let's buy a big ass battery. Battery does give you advantage. And again, you might still have small batteries, but those will be for auxiliary load, not for main bulk load. It is unwise to store it electrochemically. You need thermal, store thermal. And same goes for lower temperature. For example, let's say anything below 500 degrees Celsius. For example, this is a nation that requires district heating. And they're like, okay, we have a lot of solar energy and a lot of wind energy. But again, demand time is not lining up. How the heck we manage it? They're like, okay, heat up a giant tub full with sand. Nothing more. It's sand. You heat it up and then you let it cool down during the night time. You do not have to do anything more than, and here's the bigger you make it, the cheaper it becomes. The bigger you make it, because the insulation per liter of volume goes down. You can experiment it for yourself. For example, let's just find the metal glass, the smallest metal glass versus the biggest metal glass. Put exact hot water into them, like 100 degrees Celsius water. You will find the smaller one cool down quicker, even though the water was exactly the same temperature. Surface area to volume ratio. These things like surface area to volume, meaning you feel like, what if I make it this much bigger? It's like, yeah, the self-discharge rate would take weeks. So that's why this is far more effective. And again, why they want to use graphite? If graphite is good, graphite is good at high temperature, and they're expensive, pure high grade graphite. They're like, yeah, just use sand. Okay, cheap and abundant. And if you do not need bonkers high temperature, what's the point? If you're going to throttle the temperature output, meaning the water that is going into the system, that is only supposed to be 100 degrees Celsius. Yeah, heating it up to 400 or 1500 degrees Celsius, yeah, you are wasting money on the ceramic tubing you would need. So that's why, right tool for the right job. And other side also, for example, that takes care of the heating part. Cool, industry, big puppy, got this. What about cooling? For example, district cooling, how will they help? Well, what if you do not run the AC during the time, but again, people need cooling? No, you run the cooling from the ice block. And the moment sun goes below the horizon, meaning air temperature is starting to come down, you turn on the chillers and voila. This is in Chicago. Been working. There are other places that are also adding it. I'm hopeful that India will add this in our first grid, district cooling plant that is in Gift City next to Ahmedabad. That might have this, basically what we call thermal energy storage, basically make ice at the night time, and voila. Don't drain transformers during daytime when it's already overloaded. So they have saved a lot of energy, for city level. That's how much energy they have saved just by offsetting it. So that is one option. Second option for a lot of Indian places is like, okay, we have solar farm, but if we have to buy batteries so we can run AC 24/7, it would be brutal. But in daytime, what if we directly run AC at the daytime from the solar energy and directly freeze ice? And ice gives us cooling throughout the night. That's far cheaper in terms of electrochemical investment, and we can keep making a bigger box. It's much cheaper to make a bigger insulated box. Even if it's not insulated, or if you make it big enough, like for example, if you drop a glacier into Sahara Desert, it will take time to melt. Drop a small ice cube, it will poof. So physics helps you in this. So these are easy way of taking care of your cooling needs. Like cool when it's optimum, or when like act as a buffer where it's like, hey, we do not know which time wind is gonna go YOLO. Run this time. Whenever that happens, like you can decouple the consumption and production with a buffer. Almost like how a water reservoir is in a dam system, is the reservoir, because again, river flow is variable, output is variable because generator will control the sluice gate, variable. So you have two variables. How the heck you control two variables? Have a buffer. These are a perfect buffer. Right tool for the right job. 500, 1500, 500 degrees, sub 500 degrees Celsius, or 0 degrees Celsius. We got this. Now, let me be very clear about this. It's the wisdom problem. Humanity's challenge with global warming is not a technological problem. It's a wisdom problem. As in, we will never ever have magical technology. For example, there are a lot of people who smoke cocaine and they think fusion is going to be that. Here's the deal. Fusion is never going to work because it will never ever, I'm saying this right now, it will never be cheap or abundant. Why? This is what happens to basically highest grade tungsten humanity has ever made that was used inside that plasma donut that you see. Yeah, there is no material known to humans that can withstand fusion grade neutron reduction. Like Fission and neutron, it's minor inconvenience. Fusion and neutron, yeah. It's like comparing 3 mega electron volt to 13 mega electron volt. Yeah, it destroys things. Tungsten gets cracked, like blah, 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 destroyed from the inside. That's why if you ever paid attention to ITER, basically that fusion plant, they're always talking like how the heck we're gonna replace the blocks, and I'm like, why the heck, like I never saw people replacing blocks in a working reactor. Oh, because the block will break apart if they did not. Their best assumption is that this puppy can last 2 years. Every 2 years you have to shut down the reactor, replace all the blocks, and then hope for the best. Like, to give you a context, like as we do more fusion, we realize that how stupid we were. This is a new plant that will be opened in Japan in order to test the material. They're gonna burn billions of more dollar to test a material that can handle that sort of neutron flux. Or actually, nothing can handle it, because again, neutron causes material change. If you bombard enough neutron, nucleus will get affected by it. So fundamentally, oh, by the way, there is also a thing where helium atoms are forced, nucleus are forced inside it. It bubbles the tungsten like paint cracking up, but it's like pure metal. So we do not know. There is no known material that can handle this long enough time. Now again, I can easily see like 1 year, 2 year, that's doable. That we expected. But not like, okay, you turn on the reactor, worry about it after like 12 years. Nah, that's not happening. So cheap and abundant, that's not happening. And war is real. Whether you like it or not, or whether you live in USA and no serious country has ever boomed you in your lifetime. It has been boomed multiple times. You had boom with each other multiple times. It's just that war is real. Meaning, if you have a Fukushima-like scenario, if you have a Chernobyl-like scenario, it could reignite. Happened, past tense. So, because here's the fundamentally, I have said that time and time again, people generally do not get it. Nuclear is a weapon technology. Treat it as such, human might take care of it. Treat it as a energy production system where like people are saying, okay, we have to improve the ROI. Yeah, it's asking for disaster. One cleanup will cost so much more. It's like, oh, by the way, this Shahid drone is like, yeah, they might need a few billion more dollars just to rebuild the sarcophagus so they can have the crane functional and they can continue the decommissioning. So fundamentally, it is what it is. Humans are what they are. You have to work within it. Like my personal quote for this is E.O. Wilson. The real problem with humanity is that it's following. We have Paleolithic emotions, medieval institution, and godlike technology. Like emotions, we're still monkeys. Medieval institution, like every mathematician knew for like at least 250 years, we cannot have the voting system that like we do. We cannot have like a first past the post, like 51% you win. Yeah, that will split the country apart. Mathematicians knew this. We have to do single transferable vote. We haven't done it almost 200 countries on the planet. So medieval institution. We know this. Mathematicians are like, bro, we wrote a book about this in 1700. We knew this mathematically. So fundamentally, this is what it is. So do not be shocked. It's like, oh, how the heck they can decide? And nobody talks about what we are doing with the nuclear waste that we have already generated. We are just out of sight, out of mind, out of it. It's like, yeah, it's not being handled properly. Many of them are leaking right now. So fundamentally, what do we seek? We seek what we call distributed, independent, low cost. All these three vectors have to be managed. And these are what we call non-negotiable. That's why I kept saying we had to turn off coal power plants because solar became cheap enough. I have no idea why the heck it did not happen in Germany. And people who live in Germany, I do have a relative there. They said like, yeah, Germany bureaucracy is you dead. So I have no idea why you hate solar so much and you bitch about everything. It's like, bro, solar is cheap. China is cheap. India is cheap. Even USA is cheaper than you. What the hell? So distributed, independent, low cost. And we have to change. And here's the tools are already there. Everything I'm talking about is already there. You can just buy it, pick up a phone, buy it. Some tuning may require, but like it's a done deal. It's just that question is, will we choose to do it or not? Or we can just like, go on our merry way and then cook ourselves. But that's up to you. Again, you have to work within a human constraint. Work around it. And again, that's why distributed, more jobs, even though that may reduce the overall effectiveness, it will be far more human centric, which again, that's desirable necessity at this point in time. So this was my presentation on basically how can we actually solve the problem. Energy mix is the answer. Hopefully you have liked it, learned from it. In that case, please hit the like button, share it amongst friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike. Press it twice to show me excess disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free. And as always, thanks for watching. Press the hype button if you have liked it.